Good morning. Welcome to this session on HPC Technologies. The first talk up is Andy Rabagliati. Everyone, I'm sure, knows who he is, so he needs no introductions. Off you go, Andy.
Good morning. My name is Andy Rabagliati,
And
and I'm here to introduce you today to my SIMD serial processor. This is a single instruction multiple data architecture that looks at putting a serial CPU right onto the memory chip itself. My FPGA implementation is a test bed for instruction sets and for the SIMD algorithms. Let's run over the differences between this and conventional microprocessors. On the left, we have today's CPUs that have the program sequencer and the arithmetic logic unit in one chip, which is the microprocessor, and they talk across a bus to the data memory. So the ALU goes through the process of fetching data out of the data memory, doing the processing, and storing the results back into the data memory. In contrast, on the right-hand side, my SIMD processor organizes the chip boundaries differently. Here you can see that the ALU has been slipped into the data RAM itself. So the sequencer and program memory are still outside, but the ALU now has its own private bus to its own private data. This data, for instance, for a 4 gigabit RAM chip, would be 64,000 on a side, and the ALU means that there are 64,000 ALUs with a 64,000 bit bus wide between all of those ALUs and the data. The sequencer here will broadcast all the instructions to all of the ALUs, and the ALUs will talk to their own data and pull the data out, do the processing in the ALU, and then store the data back in the data memory. The ALUs in today's processors might run up to 8 or 16 cores into the CPU itself. The SIMD processor over here is only getting started in the thousands. So it will be thousands or even millions wide, and needs algorithms that match the architecture. What are the consequences of this? There's a massive increase in the ALU data bandwidth. Instead of a 64-bit bus to your memory, we now have 64,000 bits on each RAM chip between the ALU and the associated memory. There is a corresponding power decrease because the data does not have to be driven across pins and traces on the motherboard between the CPU and the DIMM memory chips on your motherboard. The bit serial arithmetic that will be done because of the single bit CPU in the memory chips results in the data in the RAM being transposed. What this all is coming down to is that the memory chips themselves are being harnessed for the computation. New algorithms are required. The basis of this coprocessor, this is not going to be taking over your desktop or doing much of your other work. This is a specialist processor for parallel programming tasks. And if you're not talking 1,000 way or 1,000,000 way, then this is not an appropriate machine. However, if you can look at the problem that needs to be solved and see a place within that code where thousands or millions of the same operation are taking place, then it's possible that that application might map onto this computer architecture. Everything in the machine is done in software. It's a bit serial machine, so add, subtract, multiply, divide are all handled in software. not only is the processing need to be done, but the data needs to be moved around. It has to be lined up. It has to be matched up with the operands it needs to work with. And I see the conventional microprocessor being used connected to this standard memory chip via the standard memory lines, and the host processor block move is what is going to be used for the communications on this system. There is a single bit ALU on this machine. So a single bit means that it's got two operands. We're talking simple AND or invert, exclusive OR operations. I have also added a full adder on the side, which has 3 inputs and 2 outputs, which are the sum and the carry. It has a 6-deep stack. The stack is needed for holding intermediate results during the processing. And each processor has a processor enable, so you can on a per processor basis you can include the ALU in the operation, or you can mask it. Hacker's Delight is a beautiful little collection of programming tricks, and from this I pulled out the transpose operation, which I had to code up, and also the single bit ALU, which I call the Hacker's Delight ALU. It takes 2 inputs, X and Y, and produces a single result, which is Z, and it has all of the logical operations and or invert and 0 and 1. This is the Verilog layout. This is the tiny piece of silicon that needs to be put onto each memory chip at the end of each data row. So there is a slice of these in our hypothetical 4 gigabit RAM chip I mentioned earlier. There will be 64,000 of these lined up down the side of the memory array. On my machine I have 1024 in my 1K deep CPU. We also need a sequencer to be able to manage all of these instructions. It has to be able to put together the instructions needed for the SIMD machine, and I use a FPGA 4th CPU, which is FreeBSD licensed by James Bowman, which he calls the J1, and I have extended the instruction set to execute all of my SIMD instructions. The implementation is on an RTX 35T FPGA. I've got the development board there on the left with some other bits and pieces, and on the right this is the layout of the Xilinx the array inside the chip itself, which shows the gate layout of the 1000 by 1000 memory array and the sequencer. This here is the code that is going to be executed on this machine. This is written in 4th. This is a 4th processor. It's a stack-oriented language, and where you see percents in the code, the percent is by and large a SIMD instruction. So here we're defining an add instruction which will add the X and Z operands, and we specify the number of bits for each of them. This %0, for instance, specifies one of 2 constants that can be loaded, either 0 or 1, so this is 0. This line here is where most of the work is being done. So what we're doing is we're fetching a value, a single bit, from the X operand. We are fetching a result from the Z operand. We are using add with carry, and we are writing the result into the Z register, and then we are incrementing the Z register. We have left the carry on the stack, and when we go around, the carry will be used again for the next bit as it goes through. The looping arrangement here is standard 4th and is managed by the J1 CPU. The fourth needs library routines for add, subtract, multiply, and divide. We will need vector-vector and vector scalar routines for these. And all of these routines have bit width parameters for all of their operands. To interface this and to make it easier to work with, I hooked it up to a Raspberry Pi. The Raspberry Pi has the SPI, the serial peripheral interface, that links between the Raspberry Pi and the field programmable gate array. It has two channels, one as a command channel for the sequencer to tell it which set of instructions to be running now, and there is a data channel which is for data load and unload to and from the memory itself. The templates I have here for add, subtract, multiply, and divide is the code which is running on the Raspberry Pi, which is telling the J1 fourth processor what to do on the other end of the SPI interface. The prime number algorithm itself. So what I'm going to be doing here is I'm leveraging the vector divide instruction. What I'm doing is I'm dividing all of the currently known prime numbers into my candidate number. So I've got a candidate I'm going to be testing for primality. So I will be simultaneously dividing all the prime numbers that I've generated so far into this number, and I'm looking at the remainder. And I'm looking to see if there are any remainders which equal 0, which means there is an exact division of one of the primes into this number, which of course will disqualify it as a prime number. So if I find on my candidate that there is no remainder of 0, then I go through the process of adding this candidate to my list of primes, and then this candidate will be used in the vector divide for the next number. This is the code which is written in Python. So this is the code which is running on the Raspberry Pi and talking via SPI down to the fourth J1 CPU, and it executes the algorithm that I specified previously. This can also be slow because the Python on the Raspberry Pi is doing some other work, and the serial interface and the non-pipeline nature of the communications means that I also wrote it in forth. So now here's a prime number algorithm which is running directly on the sequencer itself, and this runs a great deal faster than the one orchestrated by the Raspberry Pi. I have a demo of both of these programs running, and what it does is the Raspberry Pi runs first, and you can see the operation there, and then the second one, the Raspberry Pi tells the J1 CPU to run all the code itself, and then at the end it will pull the results out so that we can inspect the answers. Here we have the demo phase of my single instruction multiple data machine. It's all built inside a Xilinx FPGA, which is on my Digilant development board over here. Everything from the fourth executive to the memory SIMD machine. It is talking via an SPI cable to a Raspberry Pi sitting in this beautiful little laptop here. And then I have a connection into the laptop from a terminal, and this is the terminal. So for demonstration purposes at the beginning, I'm going to ask it to calculate whether numbers up to the value of 22 and whether they're prime. It goes through and it runs through the numbers there, and I'm going to ask it specifically what commands it's sending to the SIMD machine. And as you can see, it's testing these various numbers, and some of the numbers have a nil check of false, and some of them have a nil check of true. If it's true, it's a prime number, and the nil check of false, which says that there's a remainder of 0 in one of the divisions, says that it is therefore not a prime.
Now that is just for 22 numbers. I'm going to now ask it to run up to 9,000 numbers. And if you go back to the SIMD machine over here, you can see that it's doing the calculations. Now the red active light at the bottom there, as you can see, it's quite busy, and what's happening here is that it's being restricted in its speed by the link to the Raspberry Pi. So the Raspberry Pi is managing all of this via Python. So instead of using the Raspberry Pi, I'm now going to ask it just to calculate using Forth. And the Forth will be directly on the SIMD machine itself. And if we look at the 9,000 again, it goes through and it much more quickly calculates those. And instead of just 9,000, I'm just going to go up to 100,000. And if we do that and we look at it, it goes through. And it takes about 12 seconds to calculate the 100,000 primes, and then it brings the results back. Now, how do we know that these primes are correct? What we have is I have a file from MIT that lists the first 10,000 primes. This is easily accessible on their web page. And what we're going to do is we're going to compare this file with the numbers that are generated on my SIMD machine. And to do that, we will send these results to a file. And over here, it's doing the calculations again. And at the end of all the calculations, the Raspberry Pi will pull the results out of the memory of the SIMD machine. And then what we can do is we can compare those two files, the one that is generated by the SIMD machine and the one from MIT. And we will see that there are only a few differences. The MIT has a header on it with these plus signs at the front, and I've calculated just a single extra prime at the end here, but otherwise all the numbers in between are the same. So that's the end of my demonstration of running prime calculations on my SIMD machine.
What is the status so far? We have been able to demonstrate a SIMD ALU that we can put on every RAM row on our chips. We have seen it execute a moderately complicated algorithm to calculate prime numbers, and what we have is we have an orders of magnitude speed increase possible on highly parallel algorithms. The algorithms and the programs that we need to write for the SIMD engine to take advantage of it will require a fresh look at the problems that need to be solved. Movement of data is definitely a critical path in a machine like this. What is the future? The future is that the supercomputer is moving into the RAM chip. The bandwidth and low power that this provides means that it's an inevitable move. What we need to do is we need to standardize the SIMD ALU block so that if different manufacturers put the same thing into their RAM chips, that they're all compatible. We need some data movement primitives in order to investigate how things like matrix operations are going to be done on a machine like this, and we can look at tweaks for speed that will allow us to use the pin bandwidth on the memory chips themselves exclusively for data movement, where the data processing can happen in parallel while the data is being moved in and out. We need new algorithms for basics like matrix operations and filters. We need to rewrite today's algorithms to be able to use these massive parallel machines. Thank you very much.
Shot Andy for your video. Can you hear me, Andy? No, you can't hear me. Andy, can you hear me? No. Oh, right. Andy, oh, there we go. So Andy, cool talk.
Yes, I think I can.
Okay, so there's one question online. I'm not sure who from. Can you read it? Can you see the question? We want to read it to you.
No, I can't.
Andy, can you hear me? There's a weird echo there with you.
I can't hear you now. Yeah.
Andy. Oh, there's a massive delay between. Okay, there's a huge delay between the live feed and the Zoom channel.
Yes, I can try it again.
Okay, so there's one question online. I'm not sure who from. Can you read it?
Yes, I see that. In the during the slides, there's a couple of
weird echo there. There's a huge delay between the live feed and the Zoom channel.
Yes, I can try it again.
Okay, so there's one question online. I'm not sure who from. Can you read it?
Yes, I see that. In the during the slides, there's a couple of I killed all my browsers. Does that work?
That seems better.
Yes, that should. Can you hear me now? Hello?
Yeah, we can hear you.
Okay, I'm sorry. The speed of the machine is I measure it in cycles. And the cycles is basically dependent on the bit width of the operands. For a multiply, it's of the order of 1,000 cycles. Can you hear me?
Yeah.
The multiply for 16 bits is around 1,000 cycles. The cycles I'm measuring are the SIMD cycles. The J1 CPU cycles I'm not counting because it's basically straight line code, and I haven't optimized the CPU.
Cool. Are there any other questions? Oh, yeah, I've got some messages here. Okay, I have one question. I mean, it's been a long time since I played with prime numbers on a PC and stuff. How does it compare to a high-end CPU?
I haven't looked at that, but I haven't done a straight comparison. My system that I have is only 1,000 wide. I see this as if we pick it up, it will go to many more than that. So the speed is for each candidate number that I'm testing for primality, it takes constant time because all the divisions happen at once. So depending on how far you're going and how many primes you're testing, each of my primes is a constant time. Whereas on a standard machine, then for the next prime, you need to test all the new, it will take a longer time for each next candidate. Whereas mine is a fixed time for each candidate. So it depends how many you're testing. If you just go far enough, then mine will be quicker.
And your limitation is the size of your current FPGA, or
my
just
limitation currently is the size of the FPGA. What I'm looking at is putting that slice onto perhaps a RAM chip. And if you put it onto a RAM chip, then we're looking at the square root of the RAM chip size as the number, and not just
right. Okay. It looks like you've had a lot of fun.
Thanks.
Are there any other questions? It's kind of weird. I only see like 6 people, but I think everyone's on the webcast. Okay, no more. Well, thanks, Andy, for a great talk. There are no more questions. And hopefully you get some nice big FPGAs.
Okay, all right. Thanks a lot. Okay, cheers.
Well, hang on, sorry, we have one here. Have you considered other number theory sieves, e.g. lemma?
I have not done really any other algorithms except this. I was worried that I wasn't even going to get this running by this talk, but I see the next operations needed for this is basic operations like matrix multiply. The prime number one was something that I could see that could easily go parallel, but indeed there are lots of other algorithms that could be parallelized. When I started this, I actually had the wrong prime number algorithm. I was putting all the numbers into the array and then I was feeding it with my divisors, whereas I've decided that it's much better to put the divisors into the array and then feed it the candidate numbers. So it does require a completely different approach to algorithm design, because you're starting with massive parallelism and you're trying to be able to use that.
Okay, so I don't think there's any more questions. Lots of potential for bitwise image processing codecs, etc. from Kevin.
Yes, it's basically looking at where can we find all of these, like a million operations that all can happen at once, and leveraging off of that. But for sure, you don't even need to think of it as bitwise. You're just looking at image processing, but you're just looking at a single instruction stream managing all of the image or all of the images.
I mean, not related to your talk, but whatever happened to those Intel FPGAs on a single die? Because that would fit in nicely for this stuff, right?
The Intel on FPGA, I don't
so
know.
there was a proposal to put FPGA, because that's why Intel bought. Who did they buy? They bought somebody, and then they were going to put it all on one die. I don't know. It would be a nice candidate for this on those processors. So they have a CPU
like
on the same die.
Scale FPGA.
Yeah, right next to the CPU. I mean, it seems to have been very quiet.
It needs to be. You basically have to get away from shipping your data across pin.
Yeah. So Intel bought Altera. That's it. That was a couple of years ago.
Well, I look at this, the candidate for this, even though I'm building it on an FPGA, I don't see the FPGA as the target. I think the target is a RAM chip.
Yeah, sure. Well, you got a very nice talk. Thank you from Kevin. I think that's everyone. So if there's no more questions, go on. Thanks, Andy, for a great talk. It seems everyone enjoyed it. And hope to see you again in Cape Town soon.
All right, good stuff. I'd
Cheers.
like to see you. Cheers.
Cheers. Okay, Yaniv, we've got 1 minute to go for your talk, or before your talk's supposed to start. So relax.
Thanks.
So, sorry? Oh, okay. So here's now our second talk, FPGA acceleration of, I had to look up what GWAS is, genome-wide acceleration, for permutation testing. So if anyone wants to know why the world has got lockdowns in South Africa, it's because our genome testing is too fast, apparently. Anyway, so yeah. Yaniv, go ahead. Good luck with the talk. Thanks.
Thanks. Hi, everyone. Thanks for attending this presentation. My name is Yaniv Swiel, and I'm going to talk about the research that I did for my master's in engineering at WITS under the supervision of Scott Hazelhurst and Mitchell Cox. My research looked at the use of FPGAs to accelerate GWAS permutation testing. There's quite a lot of genomic, statistical, and computational background information that goes into understanding the problem. So please bear with me as I try to give you a quick overview of the theory before diving into the implementation details and the results. The genomes of any two individuals of the same species are 99.9% identical. Genetic variants, or specific locations in the genome that differ amongst members of a population, give rise to different traits or phenotypes. Almost all animals, including humans, are diploid organisms, meaning that most of our cells contain two copies of our genome, one inherited from each parent. When referring to a genetic variant, we generally mean the combination of the two variants inherited from our parents. Genomics researchers work with the concept of a reference genome, which is a representative model of a species genome that helps to standardize genomics research. A typical human genome has 4 to 5 million sites, which differ from the human reference genome. The majority of genetic variants have no known effect. Some variants give rise to benign phenotypes like eye or hair color, or can even convey positive effects, such as immunity to a disease. Other variants, however, can predispose individuals to a disease, affect their response to a drug, or directly cause a disease by affecting cellular function. Genome-wide association studies, or GWASs, analyze genetic variation over the genomes of many individuals in order to identify variants associated with specific phenotypes. Associated variants can then be studied in more detail so as to gain a greater understanding of the genetic basis of the phenotype. GWASs have been widely applied to the association of genetic variants with complex human diseases, including type 2 diabetes, heart disease, and various types of cancers. The most common type of genetic variant is the single nucleotide polymorphism, or SNP. A SNP is a single nucleotide deviation from the reference genome, as shown in this figure. GWASs typically include millions of SNPs to increase the chance of detecting associated variants and to more easily pinpoint interesting regions of the genome. GWASs usually test each SNP for association under the null hypothesis that the SNP has no effect on the phenotype. Association testing is carried out with a standard statistical test, such as the chi-squared test or linear regression. The figure on the right shows how a vector of phenotypes and a matrix of SNP genotypes are used to calculate the effect size of each SNP in the study. A p-value is then computed using a test statistic to determine whether each result is statistically significant. GWASs that use linear regression for association testing use the F statistic, which measures the goodness of fit of the linear regression model. The null hypothesis is rejected when the p-value falls below an arbitrary predetermined level called the alpha value, which is usually set at 0.05 by convention. Rejection of the null hypothesis implies that some form of association exists between genotype and phenotype. Using an alpha value of 0.05 means that 5% of the time, the null hypothesis is rejected when it should not be, and a false association occurs. Including more SNPs in a GWAS increases the chance of finding associated SNPs, but performing millions of simultaneous hypothesis tests results in many false associations happening by chance. Using an alpha value of 0.05 can result in thousands of false positives. So GWASs use a very small alpha value. Research into common SNPs has seen an alpha value of 5 times 10 to the negative 8 being accepted as standard for GWASs independent of the number of SNPs. Overly conservative control of the false positive rate leads to more missed associations, so GWASs employ a variety of methods to maximize the number of true associations. Knowing the true null distribution of the data lets us control the number of false positives more effectively. Using the F statistic to generate a p-value implies that the data is sampled from the F distribution, which may not be true. Permutation testing does not make any assumptions about the distribution of the data. It simulates the null distribution of the test statistics using the observed data by repeatedly permuting the phenotypes and recalculating the test statistics. An adjusted p-value can then be calculated by ranking the observed test statistic amongst the permuted test statistics. A drawback of permutation testing is its computational expense. Generating p-values with enough resolution to compare against 5 times 10 to the negative 8 needs at least 20 million permutations for each SNP. Two classes of algorithms have been developed to reduce the computational burden of permutation testing. Max-T permutation testing generates a null distribution using the maximum test statistic from each permutation, which means that relatively few permutations are required to generate a representative null distribution. Adaptive permutation testing identifies and stops permuting insignificant SNPs, which allows accurate p-values to be calculated for significant SNPs. Although these algorithms have alleviated some of the computational burden of GWAS permutation testing, there is a need for a permutation testing accelerator, as the computational cost for modern GWASs remains significantly high. FPGAs are reconfigurable circuits that can implement any arbitrary digital circuit. FPGAs are very flexible and powerful chips. The CPU in your laptop can be fully simulated on an FPGA, albeit at a lower clock speed. FPGAs use lookup tables to compute Boolean logic functions using the function's truth table, as shown in this figure. Configurable logic blocks, which consist of a few lookup tables and some flip-flops, are the fundamental building blocks of an FPGA. FPGAs also contain specialized logic elements, such as distributed high-speed RAM and DSP blocks, which are used to perform fast multiply-accumulate operations. FPGAs are typically programmed using a hardware description language, which maps the flow of signals between registers. HDL is then synthesized by an automated tool to generate a hardware layout for the specified FPGA. The lower level of abstraction makes FPGA-based algorithm development much more complex than software development for CPUs or GPUs. So why FPGAs? In contrast to CPUs and GPUs, which have fixed architectures and instruction sets, FPGAs do not have a defined architecture and have to be configured to perform a specific function. The adaptability of FPGAs allows algorithms to make full use of the available hardware resources, and the fact that they don't have a fixed instruction set allows them to operate on arbitrary data types. Multi-core CPUs can process multiple threads at the same time, and GPUs have high throughput SI&D parallelism, but the inherent parallelism of FPGAs allows for parallel processing on the bit level, on the data level, and on the task level. A limitation of FPGAs is their high cost, but the availability of cloud-based FPGAs, such as those available on Amazon EC2, has made powerful FPGAs more accessible to bioinformatics labs. Another limitation of FPGAs is the high barrier to entry, as algorithm development for FPGAs is effectively a hardware design problem. An automated process called high-level synthesis, which compiles C or C++ code to an HDL, has made FPGA-based algorithm development much more accessible. Although HLS operates at a higher level of abstraction than HDL, some knowledge of the underlying hardware architecture is required to generate an effective design. In other words, an algorithm written in C or C++ cannot be directly compiled with the expectation that it will perform well or at all on the FPGA hardware. The AWS F1 instance consists of a Xilinx Vertex UltraScale Plus VU9P FPGA connected to an 8-core Intel Xeon host CPU via a PCI Express interface. A C++ host application running on the CPU uses OpenCL to communicate with and control the execution of the FPGA. The VU9P is a large FPGA with around 15 billion transistors. The VU9P dev board developed by Xilinx is $7,000 and is completely unavailable due to the global chip shortage. So AWS F1 instances have made these powerful FPGAs much more accessible. The instance also has 64 gigabytes of global memory, which is memory that is accessible by both the host CPU and the FPGA. The VU9P has about 48 megabytes of internal RAM, and the SNP data for most GWASs is too large to store in the FPGA memory, so it has to be streamed to the FPGA via global memory for each permutation. Global memory is therefore a major performance bottleneck. The FPGA therefore focuses on the design of the FPGA therefore focuses on minimizing the performance impact of transferring data via global memory. Permutation testing requires the repeated computation of the test statistic F with each permutation of the phenotype vector Y. When the phenotype vector is permuted, the denominator of rho remains constant, while the numerator changes with each permutation. The numerator of rho is a dot product between the permuted phenotype vector and a vector of SNP genotypes. As GWASs typically include millions of SNPs, each permutation requires the efficient computation of millions of dot products. SNP data is typically encoded based on the number of copies that differ from the reference genome, i.e. 0, 1, 2, or missing. With a CPU or GPU, a naive approach would be to use a byte to represent the SNP data. But the fact that FPGAs can natively operate on arbitrary data types allowed me to take advantage of the fact that SNP data can be represented with a 2-bit type. The fundamental part of the permutation testing algorithm is a matrix vector multiplication between the genotype matrix and the permuted phenotype vector. For this reason, I use the FPGA only to accelerate the MVM calculation and use the host CPU for the less computationally demanding parts of the algorithm. One of the main goals of my research was to develop an MVM kernel which could accelerate the MVM computation without a significant loss of accuracy. As GWASs usually aim to identify potentially associated SNPs, rather than confirming hypotheses about specific SNPs, extreme accuracy of the MVM computation was not a primary requirement. The MVM kernel was designed to take advantage of the inherent parallelism provided by the FPGA hardware. Although the VU9P is a very large FPGA that can provide a large amount of parallelism, its resources are finite, and optimization of the hardware utilization was an important part of the design process. The width of the global memory interface is 512 bits, so the MVM kernel loops over the rows of the genotype matrix, which each represent one SNP, and processes each row in blocks of 512 bits or 256 SNP values. The innermost loop, which performs the multiply accumulate operation, is fully unrolled to fully parallelize the processing of each block of genotype data. Unrolling loops massively increases the parallelism, but also increases the hardware utilization. The middle loop, which loops over a row of the genotype matrix in 512-bit blocks, is pipelined to overlap the processing of each block. This allows one block of genotype data to be processed every clock cycle. The outer loop, which loops over the rows of the genotype matrix, is not pipelined, as the HLS compiler would attempt to unroll the intermediate loop, which would induce data dependencies and significantly increase the hardware utilization of the kernel. The VU9P has 4 banks of global memory, so I instantiated 4 identical MVM kernels on the FPGA and connected each kernel to one of the 4 memory banks to maximize the global memory bandwidth. I also found that additional kernels did not lead to an increase in performance. The host application uses data blocking to maximize the global memory bandwidth. As illustrated by this graph, global memory bandwidth is affected by the size of the buffer being transferred. So the host application blocks the dataset based on the optimal buffer size, which determines the number of kernel invocations for each permutation. This figure shows how the host application blocks a GWAS dataset and distributes each block amongst the kernels. The concurrent execution of kernels helps to maximize the global memory bandwidth and reduce the FPGA idle time. The host application also uses multi-threading to start a new permutation while the result of previous permutations are being processed to further reduce the idle time of the FPGA hardware. We compared the performance of the FPGA accelerated algorithms to Plink, which is a popular CPU-based GWAS tool that implements both MaxT and adaptive permutation testing. FPGA testing was done on an AWS EC2 F1 2x large instance, and Plink testing was done on the VITS cluster, which consists of 40 Intel Xeon CPU cores per node. 2 datasets were used for testing: a simulated dataset of 1.9 million SNPs sampled from just over 2,000 individuals, and then a much larger real dataset of 13.7 million SNPs sampled from 3,652 individuals. These graphs compare the runtime of the FPGA-based MaxT algorithm to Plink, parallelized over 40 CPU cores. I also compared the FPGA runtime to Plink, parallelized over 200, and 400 CPU cores for dataset 1. These graphs show that the FPGA accelerator is significantly faster than Plink for any amount of permutations. You can also see that highly parallelized Plink is still significantly slower than the FPGA-based implementation. Plink took 2 weeks to perform 2,000 permutations of dataset 2, while the FPGA-based algorithm took about 42 minutes. For dataset 1, Plink needed almost a day to complete 2,000 permutations, while the FPGA-based algorithm was done before I could finish making a cup of coffee. These graphs compare the runtime of the FPGA-based adaptive permutation algorithm to Plink, parallelized over 40 CPU cores. You can see that the speed up achieved for the adaptive permutation algorithm is less than that of the max-T algorithm, which is because of a reduction in the efficiency of the accelerator caused by the use of a suboptimal buffer size when most of the SNPs have been dropped. In spite of this, the FPGA accelerated algorithm is significantly faster than Plink for any amount of permutations. Plink needed 8.5 days to complete 100 million permutations of dataset 2, while the FPGA-based algorithm was done in about 5.5 hours. To show that the accelerator can effectively speed up permutation testing, a run of 700 million adaptive permutations was done on dataset 2. This graph shows that the FPGA runtime for 700 million permutations is significantly less than Plink's runtime for 100 million permutations. FPGA acceleration therefore enables the handling of workloads which are almost unfeasible for CPUs. You can also see that the low runtime of the FPGA-based algorithm makes GWAS analysis using cloud-based FPGAs quite affordable, particularly when spot instances are used. As part of my research, I developed an FPGA-based tool to accelerate GWAS permutation testing on EC2 F1 instances. The tool consists of 3 components: the FPGA design, the C++ host application, and a Python script which calculates phenotype residuals and runs the host application. The tool handles Plink formatted files to improve accessibility, as they are an industry standard method of handling GWAS data. An AMI or Amazon Machine Image is available to simplify the instance setup, and all the code developed for the tool is available and documented on a GitHub repo, which will hopefully allow others to contribute to improving its features. In summary, genome-wide association studies help us to understand the genetic mechanisms underpinning complex diseases. Permutation testing is an accurate method of removing any assumptions about the distribution of the data in a GWAS, but it is extremely computationally expensive, which means that genomics research can take a really long time. We have developed a cheap and easy to use tool that significantly accelerates GWAS permutation testing. We hope that the accessibility of the tool allows people to easily accelerate their research, and we hope that the massive acceleration provided by the use of FPGAs can open up new possibilities for genomics research by enabling permutation testing for large and varied datasets. Thank you.
Thanks, Yaniv, for a nice talk. Are there any questions? I don't see anything up here. I'm just looking. None. I have a question. I mean, why would you ever even bother going back to a CPU analysis, right?
Yeah, I mean, like that's a thing. So this massive acceleration that we get out of the use of FPGAs, it's basically, it can revolutionize this research and can really speed up this research. The only difficulty is the barrier to entry, but I hope that this tool it's easy enough to use. It's a command line application that it takes a line to perform an analysis. It's just the barrier of people using AWS EC2, which may be slightly complicated, but I've also tried to simplify that with providing the AMI, which can hopefully improve the accessibility. But there's also the barrier of copying your data to AWS and things like that. which is the only real barrier. FPGAs, I mean, if an analysis goes like more than a week or two, then the cost can get pretty high. But if you're running it for a few days, especially if you use spot instances, it can be like there is no reason to use a CPU at that point.
Okay, fair enough. Are there any other questions before I ask another one? Gone. I mean, I'm in physics, right? I don't do genome research, but when you give that example of, I think was it 7 million or 70 million things you tested in 5.5 days or something?
13.7 million.
13.7 million. Is that like a month's work of analysis after that, or is that kind of like you do that once a week kind of thing?
Well, you see, this is the thing. So with the CPU, you could run this analysis and it could take you a month. With an FPGA, it can take you a day and a half. So then it enables people to play around with their data sets and do different analyses. Whereas previously, you're running on a CPU, then the CPU crashes, you lose your results for the last week and a half, basically, and then you have to start the analysis all over again. So I think it can really revolutionize the way people do research. Just this massive acceleration can really change how people do this genomics research and open up a whole lot of different possibilities for the way people do research.
Yeah, I mean, it's cool work. Yeah. No questions yet. Well, I suppose we can wait a while for some questions other than me.
Yeah, thanks for asking some questions.
I'm curious. I mean, yeah. Well, okay. While there's no other questions, so you actually did the whole VHDL yourself, or did you do one of those System C things?
Yeah, I did the HLS because I'm a software engineer. I don't really have any hardware design experience, and I came into this research with no hardware design. I'd never touched an FPGA before I started my master's, and Xilinx I think are really trying to make FPGA design more accessible. So there's a lot of tools that you can develop in C or C++ and use this HLS, this high-level synthesis, to compile to a VHDL or a Verilog design. Maybe if it's the algorithm I'm accelerating is very simple. It's a dot product. I think for more complex algorithms, it might be a bit difficult to get the kind of acceleration that I got from this basic matrix vector multiplication. But yeah, I think for a basic algorithm like this, for my purposes, it was exactly what I needed to allow me to quickly implement something without like going into the VHDL or the Verilog and trying to learn how to quickly do that to do my master's research.
Okay, no other questions. I've still got another question. I assume like at some point there's going to be a plethora of libraries to run this stuff on various FPGAs on various clouds. It's not, I mean, like you're obviously doing it from scratch, but at some point the other stuff will come along, right?
Yeah, of course. And I think Amazon is like, I think they would love to push this. And I'm sure there are companies that are developing like very similar to what I've done, but in more earlier stages of genomics research. They do have FPGA, like cloud-based FPGA services where you can upload your data and it'll perform all the analysis and you'll get a notification when your analysis is done. You can also buy a local setup, but that's prohibitively expensive at this point, but it's coming. It's definitely coming.
Cool. Okay, you've got one question. Did you like the C on FPGA tools compared to Verilog?
Yeah, I mean, for me, because I'd never touched Verilog, so I'm a software, like I'm an embedded software engineer, so I have a lot of experience with C and C++. So for me, it just gave me like a very quick way of quickly implementing something and getting something working fast. Also, like Xilinx have a lot of simulation and analysis tools for this this high-level synthesis. So yeah, for me, it just allowed me to quickly get into the meat of my research, which was accelerating this algorithm rather than trying to learn how to implement, learning how to do Verilog and things like that. But I'm sure if I needed more speed or if I needed the design to be more efficient, then maybe I would need to start looking into Verilog or VHDL. But for my use, this high-level synthesis it was perfect. And I think Xilinx is they definitely want to push this to get people using FPGAs.
At least we got one question besides me.
Yeah, thanks for that.
Oh, wait, I got another message. What is that? Oh, no further questions. Okay. Well, I think then we can thank both of our speakers. Yeah, well, Yaniv, thanks for this talk now, and Andy, thanks for your talk before. And hopefully the CHPC will get some FPGAs in the new cluster.
That would be great.
We can only dangle and hope. Eh?
Yeah.
Okay. Well, thanks, guys. Thanks very much. And on to the rest of the conference.
Cool. Thanks a lot.
Cheers.
Bye.